All right, so unlike our previous lesson where you did a lot of work before you hit the play button, here I expected you to do no work before you hit the play button, except maybe grab a notebook or something. I'd like to talk briefly about these things. Um, what do we mean when we talk about that? What does that mean? This is red, a radical 4, that's an R. It's an R. It's an R. It's an R. And it stands for radix. And I want to say it came from Germany, but I'm not positive on that. Uh, so what do we mean when we say radical 4? Well, if we could make a square, hence the name, if we could make a square whose area was 4, then radical 4 would be the length of this side right here. This is radical 4, or the square root of 4. Now you know that 2 times 2 is 4, and so radical 4 happens to be 2. And you know a whole bunch of these. You know that radical 9 is 3 and radical 16 is 4, and we could go on, like you know a bunch of those. This is the symbol for the positive square root. There are 2 square roots of 4. There are 2 numbers that square to 4, but when we write this symbol calls for the positive one. And we can extend the notion. We can come on over here in Scrapland and talk about these. How do we know what the cube root of 27 is? Well, if we built a cube whose volume was 27, then the cube root of 27 would be the length of each edge. And since you and I both know that 3 times 3 times 3 is 27, the cube root of 27 is 3. And similar ideas go for 4-dimensional and 5-dimensional and 6-dimensional figures, things like that. So you know the square root of 4, the square root of 9, and the square root of 16. What you don't know are things like the square root of 7. What in the world is the square root of 7? How big is it? Well, that's dicey. Square root of 4 is 2. Square root of 9 is 3. So the square root of 7 is between 2 and 3? That seems to make sense. Um, is it a fraction? What kind of number is the square root of 7? Is it a fraction? Like, it would seem reasonable that it's a fraction, because these are all nice whole numbers. But is it? So I bring up my fancy trusty calculator here, and I ask it what the square root of 7 is, and it decides to be a pain and tell me that it's this crazy number. Well, that doesn't seem like a fraction, because I have a fancy calculator that turns things into fractions when they're fractions, but that's not a fraction. So it's this. More specifically, it's this. And so this gives me the impression that the square root of 7 is some crazy decimal. What's it? 2.64575, and it goes on and on and on. So it doesn't appear to stop, and what's worse, it doesn't appear to repeat. And that's going to bother us. That's going to bother us. Because if we've been talking about the number systems that we've been building throughout the whole course, we started with the natural numbers. We had all the natural numbers. And these were numbers like 1 and 4 and 9. These were natural numbers, positive whole numbers. And then we made the whole numbers, and we made them by throwing 0 into the mix. And then we made the integers. And we made the integers by throwing in -1 and -4 and -27 and like that. And then we made the rational numbers. And the rational numbers were all the numbers. So all of these are rational, to be clear. All of these are rational. The rationals were set apart as those numbers whose decimals stopped or whose decimals repeated. But this doesn't feel like a situation where the decimal stops, and this doesn't feel like a situation where the decimal repeats. And so the square root of 7 is out here. It's a real number, and this is any number that can be a decimal. That's our textbook author's definition on what a real number is. If you can write it as a decimal, it's a real number. And that's all of these. All of these can be written as decimals. But these either stop or repeat. So these must not stop, and not repeat. So here's the real question. How do we know that it doesn't repeat? How do we know that the square root of 7 is not rational? How do we know that? So bring up the calculator for a moment. So you have all these decimal places. How do we know that it isn't just these places repeating over and over and over again? I mean, that's a 6, 4. Maybe this 6 is really a 5, 7. How do we know that it's not just these places repeating themselves? And so what we're going to do is we're going to actually do some pretty highfalutin math. We're going to do a proof. We're going to pretend that the square root of 7 is rational. We're going to pretend that it is. And we're going to make up a whole new world with new horizons to pursue and no one to tell us no or where to go or say we're only dreaming. And in that world, the square root of 7 is rational. And what we're going to show is that math is broken in that world. And when math is broken, we're going to say, where did we go wrong? This is where we went wrong. If the square root of 7 is rational, then the square root of 7 is a fraction. It's p over q. And p is an integer, and q is an integer. In fact, we can say that because this is positive, both of these are positive. And it's in lowest terms. That's the idea. So if this is the case, then that's the case, isn't it? And if this is the case and that is the case, then very surely that's the case, isn't it? So here's the idea. When we write out the prime factorization of p squared, there's a 7 somewhere in it. because these two numbers are the same. This number is the same as this number, and this number has a 7 as one of its prime factors. So if this number has a 7 as one of its prime factors, then this number has a 7 as one of its prime factors. And if p squared has a 7 somewhere in its prime factors, then p is a multiple of 7. And if p is a multiple of 7, then it's 7 times some integer. And if p is 7 times some integer, then this is true. And if my algebra is right, then this is true. And now we run the exact same argument on the other side. When these two numbers are equal, 7k squared is the same as q squared. There's a 7 in the prime factorization over here, so there has to be a 7 in the prime factorization over here. And that means that q is a multiple of 7. And this is where things get dicey, because we now know that p is a multiple of 7, and we know that q is a multiple of 7. But we said that p over q is in lowest terms. Do you see the problem with that? Do you see the problem with that? If p over q is in lowest terms, then there's no common factor for p and q, except that there is a common factor for p and q. And so these cannot be true if this is also true. And so math is broken. This is what we call a contradiction. And because we have a contradiction, where did we go wrong? Well, none of our algebra is bad. None of our number theory is bad. What was bad is that we pretended that the square root of 7 is rational. So, therefore, I'm so sorry. Therefore, because it is not possible to have 7 as a common factor for p and q, it must be that the square root of 7 is irrational. Done. And this holds for the square root of 7 and the square root of 2 and the square root of 3 and the square root of 5. It holds for the square roots of all the prime numbers. There are similar arguments that get you all the other irrationals. Nothing fancy here. Does this mean that we can't know what the square root of 7 is? Well, sure we could know about what the square root of 7 is. Like, we know that 2 squared is 4 and 3 squared is 9, so the square root of 7 is somewhere in between. So we take a look at 2.5 squared, and 2.5 squared is 6.25. So the square root of 7 has to be bigger than 6.25. So we pick some number between those. Well, it's probably closer to 2.6, and 2.6 squared, well, gosh, that's 52 and 1, 5.2 and 1.5, that's 6.76, so it's bigger than 2.6. And then we look at 2.7 squared, and we can narrow it down. Like, it's not terribly difficult to do. So 2.7 squared, so that's 9, carry the 4, that's an 18 and a 50, that's 7.29. So now we know it's definitely in between there. And we can play the game where we approximate what the square root of 7 is, or we can use a calculator and get it much faster. Uh, but we can only get an approximation. We Because the decimal will go on forever without ever repeating. So the best we will ever do is approximate it with a decimal. And as soon as we stop writing, uh, because there is no pattern, as soon as we stop writing, it's an approximation. As good as it is, it's an approximation. So those are things that you should know. You should know that there are some numbers that are not rational, some numbers whose decimal approximations are, whose decimal forms are infinite and non-repeating. You should know that those numbers fill in this whole area here. This is where pi is. This is where the square root of 2 is. This is where the log of 6 is. There's a whole bunch of numbers out here. In fact, there are way more numbers out here than there are in here. By far, far and away, more numbers out here than there are in here. We just don't like to talk about these because they're not nice. These are nice. We play with these all the time. Okay, that's what you need to know. That's what's important. One lesson left, and it's really just asking questions to get you ready for a final. Catch you soon.